Hello there and welcome back again. In this video, we start with the first order systems. That is, we have come to capacitors and inductors. So far, we were dealing only with current and voltage sources, dependent sources, and resistors. But now we'll have introduced capacitors and inductors as well. So, starting with a simple RC circuit, we have voltage source Vs, R, and C, and capacitor has a voltage VC. So, what is VC? Basically, this one has a constant voltage source Vs. So, just writing the differential equation, that will be in terms of, let's say, charge. So, Q plus dQ by dt times RC is equal to Vs times C. So, what's different about this circuit is it is a first order linear differential equation, and solving it by using the method which we use for linear differential equations, that is maybe multiplying by the uh, exponential term on both sides, we can integrate it directly. So, depending upon the initial condition of the capacitor, that is Vc of 0, we can have different solutions. Let's say if Vc of 0 was 0, that is the capacitor was initially uncharged. So this will give a solution that is Vc of t is equal to V naught times 1 minus e power minus t by Rc. That is a charging capacitor. That is when t tends to infinity, the potential difference developed across it will be V naught. Thus, at t equals 0, there is no potential difference across. Similarly, if we take Vs equals 0, that is there is no source, but Vc of the capacitor had initial voltage, let's say V naught. So in this case, the capacitor will be a decaying capacitor circuit. So Vc of t will be equal to V naught times e power minus t by Rc. And on combining both these conditions, we'll obtain uh, a condition wherein the capacitor had some initial charge, and it is also being put in a circuit where Vs is non-zero. That is, there is also a source. So the general equation can be obtained by just superposing these two solutions. That is, Vc of t turns out to be Vs plus Vc of 0 minus Vs whole times exponential minus t by Rc. And on slightly rearranging the terms, I'll get uh, a slightly changed equation, that is Vc of t is Vs times 1 minus e power minus t by Rc plus Vc of 0 times e power minus t by Rc. Now this can be clearly seen as the sum of terms of charging and decaying circuits. And there is terminology coming up, that is the zero state response is Vs times 1 minus t exponential minus t by Rc, and the zero input response is Vc of 0 exponential minus t by Rc. Now, why is it called zero input response? Simply because that part comes from the decaying capacitor circuit, that is when there was no source. And so was for the zero state response when there was no initial charge in the capacitor. And on once again rearranging these terms, we get Vc of t is Vs plus Vc of 0 minus Vs times exponential minus t by R. Again, we have a terminology to describe this equation. That is, this Vs is the forced response, the steady state response, the particular solution of the differential equation. Forced response because it was forced by the voltage source of the circuit. Steady state response because it is what remains after an infinite time. That is when the second term dies out, and the particular solution. And the second term of this equation is what we call the natural response. Natural response because of the exponential term, transient response because it is changing with time, and the solution to the homogeneous equation because that's what we get when there is no source. That is the general solution. And this can also be observed that Vc in general can be represented as Vc of infinity plus Vc of 0 minus Vc of infinity times exponential minus t by Rc. So that is when t equals 0, it will give Vc of 0, and when t equals infinite, it gives Vc of infinity. This was for although this was for the capacitor, this can also be extended for the inductor. Just the equations and some constants will be different. I should also say that Rc is what we call the time constant of the RC circuit. R into C, that is the denominator of the exponential. So when we talk of inductors, the equation will change slightly. That is, uh, the potential drop across the inductor is L di by dt. So d IL by dt plus IL times 1 by L by R is equal to Vs by L. This gives a equation similar to what we saw in the capacitor equation. Uh, Instead of IL, if I write another equation in say VL, dVL by dt is plus V naught by L by R equals Vs times R by L. And on comparing the capacitor equation, which is dVc by dt plus Vc by Rc plus equals Vs by Rc, we get that the circuit is the dual of what the capacitor circuit was, just with a changed time constant, where instead of Rc, the time constant is L by R. Most of the things will remain the same. That is, the solution can again be represented as the steady state response plus the transient response. And uh, the general equation, which I just said, the this Vc of infinity and Vc of zero, just with the same changed time constant, will be applicable for the inductor as well. Now, what if the circuit is something like this one, the first circuit on this page? So it is indeed still a first order differential equation because the order of the circuit is the number of independent state variables that we can assign to the system. The two capacitors, although they might have different initial voltages, they are governed and restricted by the Kirchhoff's voltage law. If let's say um, we say the voltage source is a step function, that is, it steps to a certain constant value at t equals 0 and is 0 behind t equals 0. So both the capacitors, uh, the voltage that they might have for t less than 0 is always controlled and restricted by the KVL. So indeed, we don't have two independent state variables, two independent voltages of the capacitor. So it is a first order differential equation. Whereas the second figure on this page, it can indeed have two different voltages, initial voltages, and it is the second order. So talking of this circuit, which we started with, there are two capacitors and there is a voltage source, and as I said, it was a step function, and since it is a step function, just after t equals 0, there will be an impulsive current flowing through the circuit. The impulsive current will not go through the resistor; it will flow through both the capacitors initially. Afterwards, it will start going through the resistor. But what will happen is, since the capacitors are in series, the charge across them should be the same since they are in series at just at t equals 0. So um, once the Vs steps up to, let's say, its value, let's say its value becomes Vs after t equals 0, then this voltage will be distributed between both the capacitors such that the charge remains the same. Charge is Q equals Cv. So V1 C1 equals V2 C2. And given this, we have voltage distributed across them as C1 times C plus C1, where C and C1 were the capacitances, times V1 plus this is for the C capacitor, and for the C1 capacitor it should be C by C plus C1 times Vs. That's how it is. And in case the capacitor also has some initial voltage, uh, just now what I said was when it did not have any initial voltage, but what if it does? So in that case, the new voltage, it will just be added up to the initial voltage. As you can see in this example, just after the impulse, I have written that Vc becomes Vc plus C1 upon C plus C1 times Vs. Although, yeah, Vc and Vc1 will be related by the KVL, but this is to illustrate that new voltage will just get added up. Uh, yeah, and this is how voltage across the capacitor can abruptly change if there is something like a system, something like this. It will exponentially, I mean, just with the step of the input voltage, capacitor voltage will also rise up. So this was all with constant current and constant voltage sources applied to the circuits with memory. In the next video, we'll discuss what happens if the sources are time varying. So thanks for watching and see you there.